Thermite is, in the old-fashioned thermite, is a mixture of pulverized aluminum and pulverized rust. And if you can get this mixture to react, which is not so easy, it produces tremendous heat, and this is what you call an incendiary. An incendiary is something which can be used to destroy something by the means of heat, while an explosive is something which acts with pressure. It knocks things apart. Now, the old-fashioned incendiary is not an explosive, but it is still used for military purposes for melting iron structures.
In the case of thermite cutting charges, you would have heard far less noise, since they are worked by thermal heating, melting of the steel, rather than an explosive cutting as in RDX charges.
The thing that most struck me about the 9/11 incident was, following the incident, how overflights had detected with infrared camera 1400-degree Fahrenheit hotspots on the surface of ground zero. And that being there for a week, indicates that there was something very hot going on below the surface.
I remember an explosion. At that point, I got knocked out. I don't remember anything. Then I got up, and I remember walking out, and it was total darkness in the car doors. And I was at the edge. I was in a dentist office because there was dentist chairs and tools. And I looked out the window because the windows exploded, and the street below caved in. The whole street caved in. You can see below the street. And at that point, there was like fireballs coming up. So I said, all right, I'm not going to make it.
According to USGS, they found as much as 6% of the World Trade Center dust consisted of tiny, previously molten iron spheres. What does this tell us about the temperatures generated in the tower's destruction?
When the USGS collected samples of the World Trade Center dust, they found the iron microspheres. Insofar, the USGS does not have a valid explanation for the presence of these iron microspheres.
So what do the microspheres contain? Iron is the main element, and then it has smaller portions of aluminum, sulfur, a trace of manganese, a trace of potassium. Most of them are less than about a tenth of an inch in diameter, and they're spherical. And they're found in all of the dust blown out of the buildings during collapse, no matter where in Manhattan that dust is picked up.
You must have had a much hotter heat source for you to get 2,700 degrees Fahrenheit in order to melt the steel, melt the iron, to get these spheres, these molten spheres. Your heat source must be something like a chemical reaction, an exothermic chemical reaction that reacts, in the case of thermite, reacts at 4,500 degrees Fahrenheit.
But I've independently seen thermitic activity within 2 separate independent samples of World Trade Center dust.
In the World Trade Center dust, an international team of scientists find an advanced form of highly energetic nanothermite composites. What is it, and where does it come from?
My name is Niels Harrit. I have a master and a PhD in chemistry, and I'm associate professor at the University of Copenhagen, and I have been so for almost 40 years. I have published close to 60 peer-reviewed papers in the best journals, and currently I'm involved with research X-ray time-resolved spectroscopy on time scales of 1/millionth of a second. In the dust, we found what we characterize as unreacted thermitic material in the shape of some very tiny red-gray chips, which have different properties. Most importantly is they're still reacting, some of them, and in the reaction they produce molten iron, which is the prime indication of a thermitic reaction. And such a reaction can be used to destroy steel structures. What we have found is a modern version of thermite, which we call nanothermite, which is produced in a different way. It is not just two powders being mixed. The material is actually built from the atom scale up. We call it the bottom-up procedure, which is what you do in nanotechnology. This has two consequences for the nanothermite, which distinguishes it from the classical thermite. First, the ingredients are much smaller, which means they're reacting faster and they are more easily ignited.
The primary elements in the red material are aluminum, iron oxide, as well as silicon and carbon. The iron oxide appears in faceted grains, approximately 100 nanometers across. The aluminum appears in thin platelets, about 40 nanometers thick. It is the small size of the particles involved in this material that allow us to characterize it as nanothermite. In ordinary thermite, the particle size is much larger, and hence ordinary thermite is an incendiary. Whereas as the particle size becomes smaller and smaller, it can become explosive. Super thermite is sometimes called. This red material contains also a significant amount of carbon, and the formulation of nanothermite as described by National Laboratory Publications also implies the presence of carbon, very typically. The organic is used with nanothermite in order to produce gas, that is a very high pressure gas that makes the nanothermite an explosive. We do have descriptions from the Livermore National Laboratory in particular of how they fabricated this material, but to fabricate it is not so easy. This is discussed in our paper in the Open Chemical Physics Journal, published in April of 2009. So far, none of these papers have been refuted in the literature, the scientific literature. So that means they are unchallenged in the scientific sense. They stand as an indictment, really, of the official story of 9/11.
This is material that is of military use that really shouldn't be there.
Did you look for explosive residues in the dust? And they basically said, we're not going to look for explosive residues, period. So it's very sad. That's, again, unscientific not to even look. But here's what they came up with in response to my question, and David Chandler asked them a very similar question. We asked them, without talking to each other first, we asked NIST to explain why they would use, why they didn't consider the actual acceleration of World Trade Center 7. So here, and now this is looking at the roof line, and you can see this is now in the final NIST report, where they do agree and they admit that this looking at the velocity of the roof line as a function of time over 2.25 seconds, it's a straight line, very close to that. It fits very well to a straight line. And then they actually do the determination of the slope. A physics student could easily take these data, look at the delta V sub y over delta t, and you'll get the acceleration. It's linear on this plot, and you get the acceleration. Here's what NIST wrote in their final report. The slope of the velocity curve is approximately constant between 1.75 and 4 seconds. A good straight line fit to the points in this range allowed estimation of the constant downward acceleration during this time interval. This acceleration, here's the punchline, was 32.2 feet per second squared, 9.81 meters per second squared, equivalent to the acceleration of gravity g. Folks, that's the same as if I took a steel ball and dropped it. Nothing in the way. Okay? That's free fall, and they admit that. This free fall drop continued for approximately 8 stories, 32 meters, 105 feet. That means that this roof was falling for some 32 meters with nothing slowing it down.